The main goal of this video is to illustrate how to compute an area bounded by a function. In other words, a definite integral. So for example, in the picture we've shaded in the area bounded by x squared on the interval 1 to 3. We've already seen that an integral like this can be approximated using a Riemann sum. In other words, slicing into small rectangles. And in rare cases, we can even take the large n limit of the Riemann sum explicitly and obtain an exact solution. Unfortunately, that approach is unwieldy, and in the vast majority of cases, it can't even give you an exact solution to a problem. So in this video, we're going to start by deriving the basic machinery used to compute an area like this in exact form, and that tool is called the Fundamental Theorem of Calculus. In order to derive the Fundamental Theorem of Calculus, or FTC, we have to get used to the idea of an area function. On the left, we have an area function. A of x is the integral from a to x of f of t dt. And this gives the area bounded by a function little f from a to a variable endpoint x. So in the graph, we see the area shaded in all the way from an x value of a to a variable endpoint x. One of the confusing points here is that we have to use a different integration variable besides x because we're using x as the variable endpoint of the interval. But changing the symbol inside the integral from an x to a t doesn't change the value of the integral, so that's okay. So this idea takes a little bit of getting used to, but we can see, for example, that the area function evaluated at b gives us the integral from a to b of our function f. So the shaded area for a of b looks like that. It's the area bounded from a to b under the function little f. To clarify this idea, we work an example on the right. In this case, the inside function for the area function is given by little f of x equals x. And the area function is the area bounded from 2 to x, where x is the endpoint of the interval. Notice again that even though this is the function f of x equals x, when we write down the integral for the area function, we have to use a t in there because x has already been used to represent the right-hand side of the integration interval. And so in this example, we're just trying to get comfortable with area functions, and we're asked to compute the following values: big A of 3, big A of 0, the difference between big A of 5 and 4. And in each case, we want to shade in the corresponding area on the graph. So what about A of 3? When you sub in a 3 for x, that just gives us the integral from 2 to 3 of our function little f. So there's the shaded area represented by A of 3. This happens to be a trapezoid, so we can compute the area in exact form. And to get that done, you take the average of the height on the left-hand side and the right-hand side and multiply by the width. So for this area, I get 5/2. Okay, in part B, we're asked to look at A of 0. And so the shaded area corresponding to this looks something like this, but there's a subtle distinction here. If we plug in 0 for the upper limit of our integral, we're actually integrating in the wrong direction. And we can re-express this in the opposite direction as the negative of the integral from 0 to 2. Now that integral piece, that area bounded by the curve, is positive, but there's a minus sign out in front giving us a negative result in the end. So what's the magnitude of this area? Well, it's just a triangle, and it has a base of 2. So 1/2 base times height, also 2. And I need a minus sign out in front. So I end up with an area of -2 out of this. Finally, we're asked to compute big A of 5 minus big A of 4. So if I look at big A evaluated at 5, I take the area all the way from 2 to 5 under this curve. But then I want to subtract from that the area from 2 to 4. Well, what I'm left with here is the area between x equals 4 and x equals 5. And again, this is a trapezoid, so I end up with a 1/2 height at the left-hand side plus height at the right-hand side. So we're averaging the heights multiplied by the width. And this gives me an area of 4.5, or 9/2. And this idea of the area between two x values is a huge deal for deriving the Fundamental Theorem of Calculus. So I've put it in the box up here at the top. The area from a to b captured underneath this function little f is given by big A of b minus big A of a. So a difference in two values of the area function. And now we're looking at a picture of just some arbitrary function, little f. And maybe I'm interested in capturing the area on that, on the interval little a to little b. And what I'm pointing out in the picture is that if I look at a thin slice under this function, that's a little increment of area, and there's two different ways to represent it. So notice that the left end of that little slice happens at x, the right end is at x plus delta x, and the height of that little slice is going to be the y-coordinate corresponding to x, in other words, f of x. And I can represent that rectangle area in two different ways. One is to say, well, It's approximately a rectangle. We can flatten out the top without committing too much error, provided it's very thin. So one way to represent the area is going to be f of x multiplied by the rectangle width, which is delta x. Now the other way to represent the area is what we just discovered from messing around with area functions. It's the area function evaluated at the right-hand side minus the area function evaluated at the left-hand side. Now we can say these two representations of area are approximately equal. There is a small amount of error being committed in the first way of writing it because it's not exactly a rectangle. But I recognize something familiar on the right-hand side, and I'm going to go ahead and solve for little f of x. And what I'm looking at on the right-hand side looks a heck of a lot like a derivative. The only issue there is I need to take a limit as delta x approaches 0. And in that limit, our rectangle approximation becomes perfect, and that approximately equals sign becomes an equals sign. And I recognize the right-hand side of this thing as the x derivative of the area function. So it turns out that our original curve, little f, is the derivative of the area function. In other words, the area function is the antiderivative of little f. Now we combine this with the fact that the total area from little a to little b is given by a difference of area functions. And note that it doesn't matter what the starting point is for the area function. When you take that difference, you get the area bounded between little a and little b. But since a is the antiderivative of little f, it's more common to write this in the notation capital F evaluated at b minus capital F evaluated at a. And finally, we arrive at the fundamental theorem of calculus. If I'm trying to compute this integral, the area bounded by little f from a to b, apparently I just have to guess the antiderivative of little f, and I call that capital F. And then I take the difference, big F of b minus big F of a. And of course, there's a common notation for this. I could write that as an antiderivative capital F of x evaluated from a to b. So this is the solution to the area problem. And it just turns out, if you want to find the area bounded by a curve, you guess the antiderivative, evaluate across the limits of integration, and you get an exact solution. So let's loop back to our introductory example. We were trying to find the exact area bounded under the curve f of x equals x squared on the interval 1 to 3. Now the fundamental theorem of calculus is this powerful new tool for us to get this done in exact form. All we have to do is write down the antiderivative of that function and then evaluate it across the limits of integration. So we take that antiderivative and we evaluate it at the upper limit, the right-hand side of the interval. And we subtract that antiderivative evaluated at the left-hand side of the interval. And this first term gives me 27/3, which is 9. Second term gives me 1/3. Getting a common denominator, 9 is 27/3. And when I subtract 1 from that, I get 26/3. And there's our exact area bounded by the curve. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left. Or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.